Okay, so I'm going to give a little time to a couple topics that have to do with Le Chatelier's principle. So this one's called Using Le Chatelier's Principle to Predict the Result of Changing Concentration or Volume. Can't read the whole topic there. This lies squarely within the domain of a topic that we call, or a concept we call, equilibrium. All right? Now, we've dealt with equilibrium now for a couple weeks, but it's important, I think, to stop and think about what it means, okay? So equilibrium means that the concentration of the products relative to the reactants is constant. In other words, if a system's at equilibrium, the concentration of the products is not changing. Or if a system is at equilibrium, the concentration of the reactants is not changing, okay? Looks like I missed a little bracket there. Go back here, here's my bracket. Is not changing, okay? So that said, let's bring this over here. Let's establish some notation here. So first of all, we have some constant, which we're going to call an equilibrium constant, and we can express the definition of equilibrium by thinking of it as a ratio, right? So if we have some constant K, the ratio of products to reactants doesn't change, all right? And that turns out that's going to be characteristic of a particular reaction at a given temperature. All right, so we need this very much for this concept of Le Chatelier's principle. Now, also within the domain of that, and sort of consequent from that, is Le Chatelier's principle. And Le Chatelier's principle is as follows, and this is a definition which is sort of a little bit crude, but look at it here. A system that's temporarily perturbed out of equilibrium will respond in such a manner as to, and here it is, restore equilibrium, okay? A system that is not in equilibrium will try to get to equilibrium, okay? That's what Le Chatelier's principle is. So let's look at now some oops, I probably should get rid of this here. That's not helpful, is it? Let me just come here and say Control Z, 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 Z. Okay, let's get rid of this now. Okay, now let's come over here and say, let's put some meat on this skeleton. Let's say that if we have some reaction A plus B is in equilibrium with C and D, then the ratios of their concentrations, the ratio of their concentrations is K, right? So we can say K is equal to the product of the products over the product of the reactants, right? And don't forget that if we've got like a 2 in front of that C, that makes that squared, right? And likewise, if we have, let's say, a 3, so if the balanced reaction is A plus 3B is in equilibrium with 2C plus D, what's the difference here? Say it out loud. That's right. This is B cubed, okay? And so with that little sort of math trick in mind, I think we're ready to go over to the problem at hand. Let's look at this. All right, so suppose we've got some reaction, methane and hydrogen sulfide is in equilibrium with carbon disulfide and hydrogen gas, okay? But look at this. It looks like it's not a 1 to 1 to 1 to 1 ratio. It's a 1 to 2 to 1 to 4 ratio, okay? And suppose they're at equilibrium, all right, in the beginning. Now, they're perturbed. How are they perturbed? Suppose that some methane is added to the system, okay? If methane is added to the system, now we know, let me go back to here. If methane is added to the system, you know what I'm going to do? Do I have another, I don't have another one, do I? Okay, let me get rid of this one. I'm going to just come over here. And I'm going to say K for the system is equal to methane. It's the concentration of methane. And hydrogen sulfide was H2. And what else was it? Carbon disulfide, yeah. Carbon disulfide okay? And I happen to remember that this was raised to the 4th, and carbon disulfide, I think, was raised to the 2. Probably should be able to tell by looking at that. That's probably it. Let's go back over here and check it. 2 and 4, that's it, okay? So this is at equilibrium, and it's constant. I know that this is constant because that's the definition of equilibrium, okay? Now, in the first scenario, we're given, it says, I think some methane was added. Yeah, some methane is added. I'm going back and forth to the whiteboard. Hope that's not making you dizzy. So if methane is added, that means that the overall ratio is going to go up. That is, unless some of this comes down and or that goes up and that goes up, right? Can you see that? Because K, the ratio, has got to be constant. So if methane goes up, hydrogen sulfide's got to go down in order for this ratio to stay the same. Well, if it's going to go down, that means we're going to be, if hydrogen sulfide's going down, it means we're going to be pushing the reaction that way, okay? So it looks like I anticipated correctly what that's going to be. The pressure of hydrogen sulfide is going to go down, right? And the pressure of carbon disulfide is going to go up, okay? And it's going to go to the right. All right, you see that? If this goes up, and I can get that by looking at this. If this goes up, in order for this ratio to stay the same, that's going to have to go down, right? So let's go down here now. H2, if H2 is removed. Well, if H2 is removed, that means that the system's going to have to bring more H2 this way, right? So consequently, the system's going to go to the right. If H2 is removed, the system's going to go to the right, and we're going to increase CS2. That's not on there. But we're going to decrease methane. That's going to go down, and H2S is going to go down, right? Okay, let's look at the next one now. Suppose the total pressure inside the vessel is increased. Aha! If the total pressure is increased by adding some unreactive argon gas. Okay, so if the total pressure is increased, that means we're going to have to go to the side with the fewer moles, right? You see I've got 3 moles over here, 3 moles of gas over here, and 5 moles of gas over here. So if the total pressure is increased, the system's going to go to the left, right? Because we have to have fewer moles. And methane's going to increase. And H2S is also going to increase. Okay? Does that make sense? I used one more principle there, and that was that pressure is pressure scales with moles, right? As pressure goes up, moles go up. And so if we increase the pressure, we're going to need to decrease the moles. All right? All right, very good. So let's do one more practice. All right, so nitrogen, let me go back over my whiteboard. I'm going to get rid of all of this. Let me get rid of this. Boom. Okay, let's start a new one. Okay, and we'll go to green still. Okay, so K is equal to, let's come back over here, nitrogen plus 3 hydrogens give 2 ammonias. Nice clean. 2 ammonias. Ammonia was my product. Nitrogens plus 3 hydrogens, okay? So you can see that if this system's in equilibrium, if I add ammonia, then these two are going to go up, right? If I add nitrogen, this one's going to go down in order to release the pressure, and that one's going to go up. Okay, so it's always responding in a way so as to restore equilibrium. Let's go back over here. So if H2 is removed, that means we're going to need more H2 because H2 is removed. So ammonia is going to go less. Ammonia is going to go down, and if ammonia goes less, it's going to bring over more nitrogen with it. So that's going to go up, and it's going to come to the left. Okay? Now, if ammonia is added, that means that we're going to start pushing things that way, right? To relieve that pressure. So that's, both of these guys are going to go up, and it's going to go to the left, okay? Let's predict what the last one's going to be. There's 4 moles of gas over here and 2 moles of gas over here. So if the pressure goes up, it's going to go toward the fewer moles. If pressure goes down, it's going to go to the more moles, okay? The total pressure inside the vessel is decreased, okay? So if pressure goes down, it's going to go toward the size of the more moles. It's going to go to the left, and that looks like ammonia then is going to go down, okay, if pressure is decreased.